Assalamu alaikum. Good afternoon. This is Mohsen Hafiz. I'm the moderator for the next session, which we are doing in thematic area 2, inclusive water governance, exploring new pathways and perspectives. And thematic area session 2 is opportunities, needs, and challenges for achieving sustainable growth and inclusive development through the water, energy, food nexus in the Indus Basin. Let me give you a bit of this, the summary of the session. Since this morning, we have been hearing that Pakistan is facing the challenges not only on the water insecurity, but also the food insecurity, and the ecosystem is also not working very well. And then we heard the challenges of the salinity, we also heard the challenges of downstream delta, and also on the top of that one, the climate change. And so now when we are thinking about to overcome of those complex challenges, it's important to understand that one, how the different things are working it together. Because the ultimate goal of that one, the whole, the water, energy, food ecosystem nexus is how we are able to provide a better services to the people on the ground. And so when we are talking about the water security, it should not be because of the food security, it should not be also at the cost of energy security. We need to think about that one, water is a central pivot, water is a catalyst which is using for the food production, for the energy generation, and as well as for the ecosystem. And when the climate change is one of the major factors coming, so how we could make sure that the water needs are integrated for water for agriculture use, water for energy, water for environment, and those needs are met there. An important thing is in that one, we heard in the morning on that the Pakistan has a 68% of population is below 30. So we need to make sure that at least for the younger generation, and then we are talking about that the capacity enhancement of them, and then not in the nexus sector, in the context of not only a technical but social, and as well as also making sure that it's an inclusive approach there that's helping and contributing in that one, the institutional reform. This particular session which we are meeting it now is exploring the opportunities and challenges with the institutionalizing an integrated WEFE NEXUS approach within the government of Pakistan and related training educational institutions. And as well as this session will be supporting a shared vision of that one, different strategies and how we could achieve on that one for sustainable growth and inclusive development. So I have a very, I have esteemed panelists and then the keynote speaker. So let me introduce the first keynote speaker is Professor Julian Harrow. He is a chair in water engineering, mechanical engineering, aeronautical engineering, since 2013 at the University of Manchester. He is recognized as global leader in research related to water sources, planning and management, water, energy, food system, and in environmental management software. Dr. Harrow has a notable contribution in the Wise of the Climate Change Adaptation Project, leading the NSF Belmont-funded Jordan Water Security Project and the EU-funded Smart H20 project on smart metering and dynamic pricing. And he has worked extensively with many American universities and very well-known established universities as a part of international. And he also serves on IMI Board of Governors as an independent advisor to the program committee. Before I will invite Professor Julian Harrow, let me introduce also the second keynote speaker. Is a Dr. Afrin Siddiqui, who is a research scientist at MIT. She has a bachelor in mechanical engineering and master and PhD in aerospace system, all from the MIT. Her expertise is in quantitative system modeling and simulation for farming design and policy for technical system operating in natural environment. She is motivated about addressing the problems of sustainable resource use and development of efficient and equity conscious infrastructure and technology for improving human well-being. She has done extensively work in part of Indus Basin and in Africa, understanding that one, the coupling of that one, water, energy, and food security with the novel modeling and simulation methods. And she has more than 100 publications. So the plan is we'll be starting with the Professor Julian Harrow. He will be giving a 15-minute presentation that will be followed by Afrin Siddiqui, and then we'll go to the four esteemed panelists who have also joined us here. Over to you, Dr. Julian Harrow. Starts not the presentation, but introducing yourself as something which
Yeah. So, well, the work we're going to show comes out of a project called Future Dams. Aha. Okay, I think this is the slides. I think they've been scrunched, but that's okay. We'll deal with what we have. Okay. Well, thanks everyone. Thanks Mohsen for having me over. We're working together on the NEXUS Gains project, which is a project led by IMI here. So the ambition here is everyone talks about the food, energy, water, environment nexus. Are there really any benefits to this? What would Pakistan gain from this? Is it just a philosophical approach, or is there something meaningful? Is there something that could be beneficial? Well, we think it could be quite beneficial, and I'll try to convince you in 15 minutes that it's correct and that it's worth the investment. It's a big investment because if you think water is complicated, when you combine water, energy, and food, of course it becomes more complicated. So there must be benefits, there must be gains to justify the work. So I'll try to convince you that I think it's worth the gain. So all this started a few years ago. We started to make a theoretical framework for how can we seek to invest or to change management policies in systems that have water, energy, and food in a way to distribute benefits in an equitable way. So it started out as a benefit sharing approach, okay? So your idea is how can we share the benefit between these different economic sectors and the different regions that have hydropower, that have thermal cooling, that have nuclear cooling, that have irrigation. How do you share, when you give water, you're giving resources, you're giving money, right? So how do you share that across space and time? It's a very difficult topic. So how did we move from this? This was a theoretical paper. You can read it. It's open access if you take a picture. How did we go from this to the real world? Well, it took us 4 years and $3 million, but I'll show you what we did. The first thing we did is we needed a credible tool for river basins and a credible tool for power systems. Now, the problem with the Nexus is that only the water people like it. The energy people don't like it, okay? The energy people, they don't want to talk to the water people. Water people are always trying to be invited at the energy ministry, but it just doesn't work. In many countries, Pakistan is a little bit different because agricultural water supply is such an important factor. But in many countries, the energy investment and the energy infrastructure is very influential. So we needed to start with tools, analytical tools that were credible to both water engineers and to energy engineers. So let me start with water, okay? The tool that we're using, and at the end I'm going to show you some general introduction, and then I'll show you that Mohsen has invested in trying this in Pakistan. So we have this model applied in Pakistan that we've done with Asif here in the last few months. But a general introduction first. So this is your typical river basin simulation model. If you want to manage water, you need to learn to represent it on the computer, right? And this has been done over the last 50 years. Engineers, economists, and scientists have used a structure like this to represent the water system in a computer, and so you can simulate it, and it's a way to do experiments without trying to make mistakes in the real world. You can make the management or the investment mistakes in your computer. Okay, so we have a system called PyWR. Now, there are many systems. There's WEFE, there's eWater Source, there's many ways to simulate river basins. The nice one with this one is it's open source, okay? So Pakistan owns the intellectual property. Usually these are closed systems where you don't know what the computer code is. This system is designed for researchers, but it's also designed for the government, because what's very risky for the government is to invest in a decision support system or a modeling system that is some way inaccessible in the future, or that Pakistan researchers don't really have access to. So this is a very beneficial thing. Unfortunately, you can't see it, but there's an open source, there's ways that you can read about this that are cost-free. Okay, and then there's other benefits which we'll review. Okay, let me show you some examples. Let's skip the theory, okay? Let me show you first some examples from the UK, even though I don't sound like I'm from the UK, that's where I work. In fact, I live in Manchester, which has maybe 30% people from Pakistan, so I'm very familiar with Pakistan, even though I just arrived here about 7 hours ago for the first time. Right, so here's a first example of what PyWR, this is for London's water supply. We have water companies in England that are privatized, and this is what it looks like for a very simple model of a water resource system of the London water supply. You can see it has a few major reservoirs. Let me go to a slightly more complicated system. This is the east of England. You can't see the map there, but the map shows it's the east of England. This is already a different institution, so it's the same model, but it's a different institution. This is about 18 million people in the east of England decided that they didn't know how to invest in infrastructure. They didn't know which canals, which transfers, which desalination plants, which reservoirs. They didn't know what to build. There were millions of investment options, and how should they select the ones that they do? So we've been working with this regional group 10 years, patiently making the computer represent the exact system with the exact allocation rules so that they can try different investment trajectories. It's a big investment, but it's worth it because it's so much cheaper to make a mistake on the computer. If you make mistakes in the real world, it's very expensive financially and politically. This is a great way to make mistakes on your computer only. Let me show you a third example of this model for a different use case. And these are my colleagues from the University of Oxford. They've used the same model, PyWR, to build a national. Okay, nationally, there's about 7 or 8 big new reservoirs that are being considered, and they wanted to make a model that could represent the different transfers. So what I'm trying to convince you is that you have one model, it's free and open source, and it's being used for very small models, for city water supplies, for regional water, energy, food allocation, and here for national scale selection of infrastructure investments. And then here's the fourth example. Here we're using the same model, PyWR, to do optimization of 1,500 water transfer options, okay? In the United Kingdom, we can connect any regional system to any other regional system. So where should you put the pipelines? There are millions of different options, okay? And so we use PyWR to represent all the possible options and to optimize what were the least cost and most reliable combinations. Okay, those were some examples, all of the same model, PyWR, for different regulators. The previous one was the Environment Agency. This is for Ofwat, the financial regulator. And so I'm trying to convince you that this is a versatile tool that the government of Pakistan may want to consider, because I've just showed you 4 different use cases: a private water supply company, a regional planning group, multi-sector, an environment agency, this was environment agency, and this is the financial regulator. So that's 4 different institutions using different versions of the same model, okay? So hopefully you're convinced that it's versatile. Okay, let me show you some other examples. This is one that's funded by Mosin. Part of their NEXUS gains, we built a first version of the Central Asia Amu-Darya River Basin model, also with PyWR. Here's the Nile Basin. We've been working in the Nile Basin 8 years. If you think people fight about water in Pakistan, you should go to East Africa. That's serious fighting, okay? They have one river for 500 million people. That's very serious. And so there we've been working with them for many years about how to better manage the water, and being able to make exploration of the system and changes to management and investment on the computer is very useful. Here's one that we haven't used yet. We started this for the FAO 10 years ago, but then after 3 years, the governments of Iran and Turkey said, we don't want to participate in this project because it's too controversial. But luckily, we already had the data and we continued as an academic project. But we haven't used it yet because we haven't received really the license from the local governments. So we're waiting for the day when Syria, Iraq, Iran, and Turkey will come together to discuss their water management. And when they do, the model is ready, okay? This took us 6 years to build. It's a perfectly calibrated water river basin model. So just some examples, and finally the one you've been waiting for. This is one that Dr. Asif from IMI in Lahore has built in just a few weeks. And we're hoping to improve this with the help of the government and the ministry. And you can see here just a little bit more detail. So we're starting with just the main primary canals, but we'll be increasing the detail in the coming weeks. Okay, all of this, and then all these screenshots you've been noticing, you might have noticed that they're part of a website. Well, separately from the open source simulation, there's a website which you can use to, if you're not an expert in Python, you can use this waterstrategy.org. It's a free website that allows you to build and share and operate these models. Okay, it wouldn't be a water energy food nexus if we only did river basins, okay? So we spent 3 years and almost £1 million, $1.5 million, to use a similar approach for power systems, okay? You can't do the water energy food nexus if you don't simulate the power system, okay? Because the only way to investigate how water and energy can synergize is to simulate the power system. If you can't imitate the power system and understand how it works on your computer, then you can't do water energy food nexus, okay? It just doesn't work because you have nothing to offer the power system engineers. Because you say, oh, we want this hydropower to work well with your solar. And they say, okay, our solar, it turns off. Every time there's a cloud, everything shuts off. So how are you going to deal with that? Oh, I don't know. You need to be able to simulate it. Our energy power system model, this simulates with an hour time step. And we can see how the solar panels and the wind operate hour by hour in conjunction with the hydropower dams. And that's very important to do. And so you can see here how we use, all this is open source software, so that's another good thing. You know, Pakistan's researchers and consultants can adopt these tools and own them. They're not using someone else's tool. So anyways, I won't talk about the software too much, but anyway, it all works. Okay, here's an example of the work. This is the combined water in gray and power system in red, combined water energy system of the East African power pool. Okay, so that's 12 countries, all the electrical connections simulated, and all the rivers simulated, all the major reservoirs. Okay, hopefully I've convinced you that this is a serious platform to do work. Now let me show you some case studies. Okay, unfortunately we have very little time because I did too much talking. So here's the case study one, okay? The big question is, so here we have the, okay, this right here is the GERD reservoir. It's the most controversial hydropower asset it's here. It's the most controversial hydropower dam in the world. Egypt is very scared that it will prevent water from coming down. So what we wanted to know is if Egypt purchased power from Ethiopia, would that alleviate its water security concerns? And I don't have time to go into the results in detail, but what you can see here is we have a high power trade scenario. This is a scenario where Egypt is buying a lot of power from Ethiopia, and surprise, surprise, if they do that, it guarantees they have more releases and they have more water downstream. And you can see here the number of weeks in a 10-year period where the reservoir is in the normal storage range is very high in that scenario. So if you trade energy, Egypt gets more water security. It's common sense, but you can't simulate it unless you have the combined water energy simulator. You just can't answer those Nexus questions unless you've gone through the trouble of being able to represent the engineering. And so there we go. That's why they've been negotiating for 10 years and this solution has never been brought up. Why? Because if you don't have the tools to represent the water and energy synergies, then you can't talk about those solutions because you don't know about them. Okay, let me go to a next, time is moving quickly. This is another interesting system, now a more advanced application, where we're looking at investing in infrastructure in Ghana. Okay, Ghana is a West African country, and the question was, you have the solar power, you have a lot of solar power in the north, but everyone lives in the south. Okay, the big cities are in the south. So how can they connect the solar power in the north with the cities in the south? Well, the idea is to use your hydropower like a battery and maximize your solar energy, okay? And only use your hydropower as a battery when the wind and the solar fail, okay? That's the same thing Pakistan could do. If Pakistan wanted to get all this COP28 finance, right? You get the finance for infrastructure when you lower your emissions. So Pakistan is going to be very interested in using its hydropower dams differently to maximize its use of solar and wind so that it can receive better financial conditions from global finance for emissions lowering. Okay, so what we did is we took these combined water energy and we connected that integrated model with artificial intelligence. Okay, this is a more advanced, this is cutting edge research. We take our integrated water energy simulator and we connect it to an artificial intelligence optimization algorithm, okay, with these objectives. I won't go through them because I don't have time. So you can see these are all the things that the government of Pakistan would want to do. It wants to minimize operating costs, capital costs, and it wants to maximize benefits. Okay, and so I don't have much time to train you, but here you're looking at the most optimized, each line represents an investment package, okay? And so if you want to get low emissions, sorry, let me just go here. The preference is towards the top, okay? So if you had, each line represents a package of investments that's been filtered by the artificial intelligence, and the best package would be a straight line across the top, okay? It would have perfect metrics for everything. But you see, you can never have everything you want. There's crossing lines because you have trade-offs. You can never get everything perfect in life, right? If you want more of something, you have to give up something else. And that's what this plot is showing. We can discuss this more at the break, perhaps. Okay, let me skip that. If you're interested more in this case study, it's published here. If you can take a picture of that, it's an open access publication. Okay, my concluding remarks are that spatially quantifying river basin and energy system interdependencies allows presenting decision makers with actionable multi-sector benefit sharing solutions. These include policy changes, changing the rules of how water is allocated, about how water, energy, and agriculture share water, but also infrastructure investments, right? How do you prioritize investments? And then the second case study I showed you was an artificial intelligence assisted design approach to help identify strategic interventions. And this is something that Mohsen and his team will be able to do in the next couple of years as we work together. And so we're hoping to work with the government in Pakistan to be able to use it. Here is this AI approach. This paper just came out with an intriguing title, hopefully. If you'd like to read more about this multi-dimensional cost-benefit analysis, just take a picture of this open access paper and you can read about it there. Sorry for going over by 1 minute. Thank you very much.
Thank you, Julian, for sharing some of the example and see how that could be potentially beneficial for Pakistan. So that's where the IMI is working with the government of Punjab, federal government, the Ministry of Water Sources for development of those tools. And I think hopefully the next year when we are talking about the Pakistan Water Week, this tool will be practically applied and then saying we will be able to show certain results. And Julian is here for the next 3 days. And it will be, I mean, if anyone is interested, then please feel free to have a discussion with Julian. Julian, there are particularly questions which I have it, and other people will come back to you. But let's hear from the other keynote speaker, Dr. Afreen Siddiqui. And Dr. Afreen Siddiqui will be talking about an adaptive systems framework for leveraging the WEFE NEXUS in Pakistan. Over to you, Dr. Afreen.
Thank you very much. Let me see if I can share my screen here. Is my screen visible?
Yes. Please go into presentation mode. Yes, now it's visible. Thank you.
Very good. Assalamu alaikum, everyone, and hello. It's a real delight to be joining you all for Pakistan Water Week. And I'm sorry that I cannot be present in person, but hopefully you will find this presentation helpful, and I'll be happy to engage over email and online later on. So I'm a research scientist at MIT, and I work on systems modeling and analysis. And for many years, I've been analyzing the water energy food nexus in Pakistan. So as we just heard in the previous presentation by Dr. Julian, who mentioned that absolutely the water energy food ecosystems nexus has been used as a useful conceptual approach, really in the beginning, recognizing that these critical resources of water energy food are interrelated. And a lot of work historically or traditionally has examined physical resource linkages that exist between water, energy, agriculture. And those physical linkages have traditionally been examined by understanding the key segments in water such as from abstraction to treatment and purification to conveyance. Similarly for energy and similarly for agriculture, breaking these sectors down into different segments and then understanding how the resource connections exist. So for instance, we use energy to pump groundwater, and similarly we use water to generate electricity, which is the case for hydropower. These connections are well known, but in many cases are not quantified. Understanding those quantifications is the first necessary step towards improving our planning. We heard a lot of this interesting results. Thank you for the previous talk. I thought it was very interesting. And this is just one example of some early work that I had done, sort of essentially showing one of the critical resource links, very well recognized, of hydropower in Pakistan, but sort of seeing how it's distributed in terms of its operational capacity. This is for 2017. This data might look a little bit different. There has much development in the last since 2017, especially in some hydropower. But we can essentially see that there's a distribution of different types of technologies: hydropower, combined cycle, gas turbines, steam turbines, and so forth. And in some cases, such as for hydropower, we need water for generating electricity. For gas turbine and steam turbine, we actually use water for cooling. The use of water for cooling thermal power plants is actually not negligible. It is an important part, and depending on where the power plant is located, it can become actually an issue, especially in terms of drought, in times of drought, or when there's low water supplies. The use of water for cooling is primarily for withdrawal. So power plants will withdraw water, run it through the cooling cycle, and will put it back into the water or into the river. So the real need is for withdrawal, and that can be very significant. For nuclear power plants, that's especially the case. They need tremendous amounts of cooling water, but also for gas power plants. Some countries, such as the power plant withdrawals are actually 39% of the total national withdrawals, so very high. But here in Pakistan, you can sort of see how the technologies have been implemented. And actually, if you look at some of the most water-intensive technologies when it comes to power plant cooling, which are once-through cooling, OTF, and mechanical draft towers, they constitute about 30% of the installed capacity in Punjab and Sindh. So overall, by and large, if you compare it with other countries, Pakistan does not have the kinds of cooling systems that many other countries have invested in that rely a lot on freshwater withdrawals traditionally. This might change into the future, but nonetheless, this is an important issue that one needs to understand, particularly for understanding future risks in times of drought. Now, this type of analysis, helps us inform planning, particularly choices of future technologies that we want to invest in. Other analyses have also been done. Here, I'm showing you an example of earlier work also that we did. You can sort of see the date here, 2013. This was a paper we published almost a decade ago. And as far as I know, this was one of the early papers that explored how much energy are we really using in pumping groundwater for irrigation and agriculture. And in order to do that, we built actually a detailed ground-up model for Punjab at the district level, tehsil level, used agricultural machinery census data, used a lot of other data, the Pakistan Energy Handbook, a lot of other official government publications and data sources to essentially compute and compile a very detailed sort of estimate of how energy is being used on the on-farm level for agricultural operations. And for on-farm, the agricultural operations are typically, groundwater pumping, running tractors for field operations, and so forth. And this is energy that farmers have to pay for. Either they have to purchase the diesel to run their tractors or their pumps, or they have to pay the electricity bill, and so forth. So we really were interested on-farm agricultural machinery. And what you're seeing here at the bottom left are some estimated computed results that we had based on census data and other calculations, which basically showed that the use of light diesel oil had been declining year after year in the agricultural sector. The use of electricity had increased, but most importantly, the use of high-speed diesel, HSD, had increased the most, both for use in tractors as well as for groundwater pumping. But the use of HSD, as reported at that time in the energy statistics in Pakistan, were all included in the transportation sector and not in the agricultural sector, which basically hid or at least made our understanding of how much energy was actually being used for agricultural operations deficient. And what our calculations showed that up to 20% of primary energy use in Punjab was associated with on-farm agricultural operations. And of that 20%, about 12% alone was just for groundwater pumping. To give you a context, when this work was done, this was a time when there was a lot of shortages in the country for diesel, for fuel. And again, these are costs that farmers pay, so that increases the cost of production. So all of this information was very important to understand, and we hope this would guide future policy and so forth. Much has changed since that time, as we know, and more studies have come out. But what we tried to show here was the kinds of analysis that were needed to improve our planning, both for energy and water. Here in this case, as you can see, we were using a lot of energy to get water for agriculture. So your classical water, energy, food nexus. A follow-on study that was done in response to this work was actually what you're seeing on the right here. This is work I did in collaboration with IFPRI, Claudia Wingler and others, and they did very detailed surveys, on-the-ground surveys in Punjab to really understand what was driving the groundwater pumping, what were some of the key driving reasons for groundwater pumping at the farm level. And what those surveys reveal, what you're seeing on the top right, and I've sort of highlighted that the abstract here in the box, that one of the major drivers for pumping was actually the variability and uncertainty in surface water deliveries, right? So we have a large canal infrastructure which provides a lot of water, of course, for many years, but it is often the uncertainty in the water supplies when farmers don't know exactly when they will get their water supplies at the farm gate is one of the reasons why pumping ensures a reliability of water access. So one of the drivers, it turned out, was, how can we improve the reliability of the canal water system? And that in turn can potentially have a positive impact in energy consumption, right? So we can potentially lower the need for pumping and therefore energy use and therefore cost of production and all of those things. So this was one of the work we did follow on. And then following that, again, and this is work we published in 2018, about 5 years ago, what we did was to then explore, well, how can we understand the performance of the canal systems in Punjab? And here what we did was to use basically highly detailed data that is provided by the Punjab Irrigation Department. They do a very good job actually in providing, daily information about discharges, about flows in the canals. It's publicly available. It's open source, which I think is a very good thing because it allows people to have a very transparent view of how water is being delivered. And it also allows us to understand how we can do better. And that's really the motivation we had in beginning to examine, well, what is the nature of the canal delivery systems? And what you're seeing here on the top left is basically one example of 10 years of data that we looked from 2007 to 2017 at that time of the canal deliveries and the entitlements. The entitlements that are allocated for canals 6 months in advance for every season, Rabi and Kharif, and the actual deliveries that were made as reported on the publicly available portal. So the deliveries are shown in blue and the entitlements are shown in red. And we did this for all the major canals. So this data, we only looked at the canal level at that time. And in order to make sense of it, overall, you can sort of see that the red and blue in an ideal case should match perfectly. You can see that by and large, they are well aligned. But of course, so there are also some differences, and that also varies across canals. And we wanted to understand how can we make sense of this data to inform our future operations. So we came up with a series of metrics, some that have been published previously in literature, some that we made that we formulated new for this work. And essentially, the metrics were focused on this ratio of delivery to entitlements for each canal for each 10 daily period. And that's what you're seeing, this ratio alpha here. So delivery to entitlement for each canal at each 10 daily period. And then using this ratio, we ran a lot of statistics to understand the performance. And one of the statistics we used was the coefficient of variation in alpha. So coefficient of variation meaning that how does this ratio vary across the season across the different canals. And we call this the equity metric. Of course, equity is a big word. It means a lot of important things. I don't want to narrow it down to just one equation, but just to give a sense of understanding how uniformly the canals were operating or not we use this measure of coefficient of variation, and this has been used in prior literature, just to get a sense of the uniformity of operation. So if there's a shortage, are all the canals running a shortage? If there's oversupply of water, all the canals, and so forth. And then we use the reliability metric, which is the water delivered, but the delivery actually occurring at the time of for the entitlement. So there's the flow exactly matching what the entitlement was planned. And again, these entitlements are planned 6 months in advance, so it's often sometimes gets difficult to actually match the flow exactly. This is at the major canal level that I'm talking about. All of this together, we basically looked at the system, and here were some of the results that we got. If you plot the equity of network reliability on this X and Y axis in two-dimensional space, what we essentially got was ideally what you want for your equity metric to be as close to zero as possible. So you want this, below the, as low as you can on the Y axis, and you want your reliability metric to be as much on the right as possible. So 100% reliability is the ideal case. And this is what we called, in a very narrow sense, water security, right? If the entire system is 100% reliable and fully equitable, that could be one quantitative definition of water security. And this is canal irrigation that we're talking about, which is being used for agricultural production. So you can certainly see the water and the food nexus here. And when we found here data that on equity and reliability at the entire canal network level, so these are not individual canals, but these are all the major Punjab canals that you're seeing the data for, all aggregated together. But you can see over time, for the 10 years that we plotted, we could see that, it is moving, or it is sort of towards the right, which is good. So reliability is, 90% or 85% or so forth at the aggregate level, which is not too bad. Equity, you can also see sort of, changing. But one thing that was apparent from this data was that there wasn't a consistent progression that one could observe. If you compare the years, sometimes the dots would move to the right, sometimes towards the left, sometimes up or sometimes down, if you actually compare these dots over the years. So this was apparent that what in an ideal case, what we want at the system level is behavior that what we call goal seeking in a complex adaptive systems literature, goal seeking, where the system is consistently moving towards some desired state or some desired endpoint. In this case, we would like it to move towards increasing water security. And that brings me to the conceptual framing of improving water security, energy security, and food security from a complex adaptive systems perspective, which is essentially the idea that what you need to have are essentially on the left-hand side, what you're seeing is a time domain representation of a system state over time. So the black line is showing some actual state of the system, and the red line is showing a desired state. And in an ideal case, what you want is the state of the system to move close as possible to the desired level we would like it to be. So in our case, perfect water security, perfect energy security, perfect food security, right? How do we implement this kind of behavior? On the right, what you're seeing is sort of an adaptive system model, which essentially says that you want to have a structure in place, which is looking at the system state, comparing it to some desired goal that you would like the system to be at, understanding the gap or the discrepancy that exists, taking corrective actions, and then linking them back to affect the system state into the future. And you do this in a cyclical process until the system reaches the desired state. This is a classic control loop that is widely used in adaptive machines. We use this in cars, we use this in spacecraft, we use this in satellites, we use this in most modern machines. There is an adaptive, there's a control loop of this nature that is working. On the right, you can see an example of this in physical realization on how these systems actually get implemented. That they're on the top, you're seeing a controlled process. Then you're seeing sort of the state of that system being sensed by sensors, reports, information being generated. They're sent to a controller where policies, directives, decisions are made, and then actuation, which is the actual operations that are done in response, so that to the information and policies, so that the system state continues to move towards the desired state. So just to bring it back to the context that I was talking about, here's a very simple diagram. Of course, there's a lot more details that are not shown here, but just for the perspective of discussion, is a very simple diagram of how traditionally some of the canal allocation processes work, where we basically take the seasonal provincial allocations in million acre feet based on the processes of IRSA and other rules that we have. And we take the historic canal allocations, and these are used to then come up with the actual allocations for a particular season. These actual allocations are made based on the storage that we have in the dams for a given season, the expected forecast for rain and all of that. All of this is taken into account to come up with a schedule for how the major canals will be allocated in terms of water, right? And then this happens on a 6-month basis, biannual basis, and then these overall allocations are then broken down into 10 daily entitlements, right, which are then used for actual canal operation on the 10 daily level. So there are 2 different time periods that are operating at a meta scale, a 6 monthly time period and then a 10 daily time period. And then, of course, the deliveries happen based on the scheduling, and you see these inputs of noise. What are these? Well, there are all kinds of disturbances that are happening in the system, all kinds of physical disturbances, weather, technical, all of these things, which can impact the actual water that reaches the farm gate, right? And then we have the reported canal deliveries, the data that we're collecting. So all of this combined, you can observe that if by and large, this is how the process works. It is good for operations that it is enabling the surface water delivery, but how we might be able to improve is to go back to the feedback process, the adaptive systems idea, where you want to have a few important feedbacks occurring in the system where we actually take the data off the deliveries that have happened and then use them to inform future entitlements, both at the 10 daily scale as well as at the 6-month operation scale. And if we were to do that, it could potentially further improve how the system is operating, further improve the reliability, and further improve the overall performance. So essentially, by improving the social processes of feedback and governance, we might be able to improve the reliability. So no matter how much water there is in the system, we can actually improve the reliability by instituting these kinds of feedbacks, information feedbacks, and governance feedbacks. Just to give you a sense, you can actually expand this idea of feedback and adaptive systems into this bigger two circular sort of concept where the system sensing, measurement, and corrective actions are taken in the context of knowledge production and knowledge sharing, which actually can change the system goals over time. And this goes to our idea of water, energy, food security integration, where we actually can step through each of these components and understand if all of these elements are implemented in the system. Do we even have a goal to begin with? Do we have a goal for how much food security, water security, energy security are we aiming towards, and what we would like it to be over the years? Are all the actors in the system aware of this goal and therefore sharing adequate knowledge? Do we even know the existing level of water, energy, and food security, both at the household level, at the community level? Do we have the adequate monetary resources and personnel allocations to make the necessary corrective actions that are chosen? And then the actions that are chosen, are they actually being implemented? All of this has to come together, connected and operating at necessary speeds for a system to actually approach its desired state. That's the fundamental idea of complex adaptive systems. And just to end, I'm sorry, I'm a few minutes over. Just to end, I will share this picture with you, giving a conceptual idea of how basically institutional and governance linkages could, in theory, be made and implemented, where water security, food security, and energy security at the provincial level could be integrated and conceived, where we have adequate information exchange, we improve the links that are missing or not there, and also make sure that we have stated goals that we are trying to achieve. And together, by integrating these processes and these links, we can move towards improved water, energy, and food security. So I will end here. Thank you so much for your time.
Thank you very much, Dr. Afreen, for giving a very comprehensive presentation and then sharing some of the, the benefits of the open source data which is available with the Punjab Irrigation Department. This is a one small example, but then this data could be utilized much more for the other thing, for other purposes. Now we'll come back to you, Dr. Afreen, for the question, but let me also invite now my panelists, and so that we'll go through. First of all, my first panel member is Professor Rasool Bakhsh Meher. is currently serving as a Vice Chancellor at the Benazir Bhutto Shahid University of Technology and Skill Development. He has 20 years of experience in environmental services, water and wastewater treatment, as well as waste management. Over to you, Rasul Baksh Mehsab. Please join us on. My second panelist is Engineer Amar Khan, who's joining us online. And Amar Khan is the Chief of the Strategic Policy Research Policy Reform Unit, Punjab Irrigation Department. And he's also looking after that when the Punjab Water Sources Commission and Water Services Regulatory Authority, which one of the mandate of the Water Sources Commission and Water Services Regulatory Authority is how to manage that one equitable water allocation for multiple sectors, for agriculture, for industrial, for environment, and for the domestic one. And thank you for joining us online. My next panel member is Sahrash Raja. She's an economist with 9 years of dedicated experience in research and development. Currently, she is working as a research analyst at IFPRI, Pakistan. Other panel member is Engineer Nadeem Sadek. Nadeem Sadek is working as the Director General of Balochistan Agriculture Research and Development Center, Pakistan Agriculture Research Council, and based in Quetta. And Nadeem has a significant contribution towards the state irrigation management and development in Pakistan. Thank you. So let me go through that. The questions which we have, we will starting with the Rasul Baksh Meher Sahab. You have run that one, the USAID Center of Excellence in Water, in the former position. Please. Please. Let me introduce Sahrash. She is working as an associate at International Food Policy Research Institute, and she has more than 9 years of dedicated experience in research and development. So my first question is to Professor Rasul Baksh Meher. Talked about that one, typically as a irrigation engineer, then the courses are taught about that one, the hydraulic engineering, and then the water management, groundwater management, and all that one. Now we are working in the other dynamics. The problems are quite complex, and in the context of that one, the water, energy, food ecosystem, which we are talking about multidisciplinary focus. What are the needed features of the multidisciplinary focus in education to support these new approaches? How we could transfer that knowledge, how we could build that curriculum as a part of the universities to overcome those complex challenges, and then the students are well trained. Over to you.
Bismillahirrahmanirrahim. Thank you very much, Dr. Mohsin Hafiz Saab, for inviting and providing opportunity to speak on very important issue, water, energy, food, and environment. First, I want to little bit give you the background prior to give the curriculum design on this. Actually, you know, the population is increasing, and because of the population growth, there's a food requirement is increasing. And for the food, when we need a food, then for the purpose of the food, we need more water. And for the when we meet the demand for the food, then we have to abstract more groundwater, and that also bringing the consuming more energy, and energy always come with the environmental issues and impacting the environment. And also to meet the food demand, we are using more pesticides and more fertilizer. That is also impacting the environment and land degradation. And also the land salinity is increasing. So this is really the food, energy, water, and environment is very integrated subject. And nowadays, it is very much important that we should have some smart irrigation system, and with the curricula, we have to bring modification, and somehow modification we have brought, and we are teaching the students like application of IoT in the civil engineering for the flow measurement purpose, groundwater monitoring purpose, and salinity, soil and moisture purpose. We are already we have brought some amendment in the syllabus, and students, they are studying for that, how to measure the soil moisture and like groundwater level fluctuation, how we can measure. Even there are sensors are available. So with the water quality, because when farmer they more abstract groundwater, then upconing will take place, and ultimately the saline water will come up. So there are sensor, they will inform that now the water is abstracted, there is a more saline, so pump should stop. So this is now automation is also taking place. So there is a need to teach the students and train the professional engineers. Then they must be familiar with new advanced and small technology, so that can meet this our water, energy, food nexus demand.
Thank you, Sulbashmir sir, for the need of that one and how we could train to the new students for the next generation of the tools and technology. I will come back to you further on that one. Now I will be moving to the Amar concept. Amar concept, you are managing that one, the most complex irrigation system in Punjab, and you have seen that one, the two examples. First example, Professor Julian Hero talked about that one, water energy optimization and the tool which is being developed. Second example, you heard Dr. Afreen Sadiqui. She said that one, what are the challenges for the adaptive system framework and how the adaptive system framework will improve that one, the better water management, improve the system level, the equity and everything there. So the question is, you will be managing as a part of the Water Sources Commission on the water allocation system for multiple sectors, not only for agriculture, but also for the domestic, for the industrial, for the environment. What do you think about these, the tools, how those tools could helpful to you for improving your decision making, for better management of the critical resources, which is water? Over to you, sir.
Thank you very much, Dr. Mohsen Hafiz and other colleagues. I wish I could join physically, but due to some engagements here, compelling engagements, I couldn't join. But anyway, regarding this particular question and regarding this topic, few points before I precisely answer your question. I mean, we all know that we are blessed with the water is the agriculture sector is very much a privileged sector, and all our more than 92% water is being consumed for agriculture sector. But that privilege is going to lose. I mean, it's not going to be there anymore because there have been competing demands coming from other subsectors. We have competing demands coming from the industrial and commercial sectors. The drinking water requirement is increasing every day passing. There have been a privilege for the agriculture sector in the past, which is no more there, and which will remain no more in coming future as well. Dr. Julian has very rightly said, his approach was basically benefit sharing approach, and these algorithms and artificial intelligence systems and these modelings, those can help us, while making these decisions of subsectoral allocations and how to optimize, and how to get more benefit out of the various uses of water. At the same time, we should keep in mind, before we do modeling and before we make any strategic decision making, that we have large pressure of the population growth. It is not as other parts of the world, we are at a very high scale growth of our population. I mean, if we talk about Punjab, it is 240 million. And with this increasing rate of 2.4% per annum growth rate, every year we are adding 5 million people to our population, which is a huge burden, not only on the water sector, but also on the food, energy, and other subsectors as well. We started this journey for infrastructure improvements within irrigation about 20 years ago. We made a major investment in our infrastructure development projects. We made huge investment for rehabilitation and upgradation of our barrages, which is an essential structure, to deliver water to the canals. And at the same time, much has been done on the infrastructure side, but on the institutional and on the transformation side, we just started our journey. We enacted this Water Act in 2019. Its implementation is a real challenge. The Water Act, in Pakistan, we all know that there was no regulation for groundwater particularly, which is a very important source for agriculture and for other uses as well. So there was no regulation. There was ruthless abstraction of this water, over a period of time, because food and fiber demands are increasing, due to this rapid population growth. And at the same time, as Dr. Arfin said, huge bill is being paid on the account of energy, for this import of diesel and electricity on account of tube wells. So we all know that huge mushroom growth of tube wells in Punjab, about 1.2 million tube wells. We started geotagging of these tube wells. Under the Act, we have a lot more challenges coming in near future. We have to do a much more on the water conservation, we have to explore further options for beneficial use of our flood water. We have to do much more focus on our rainwater harvesting. We have to do adequate water pricing for various uses of water. These are all related to water governance issues, and Dr. Arfin rightly said, we have equity and reliability issues, at the moment, and to address those issues, Water Act is an instrument, which would provide us a real instrument for our improved water governance in Punjab. But the real challenge is that we still have to implement this Water Act. And I am thankful to IMI for providing this support to pilot test this in Okara district, which is one of our 36 districts in Punjab. We just started this, as we go along, we will do the subsectoral allocation, we will do the water conservation, we will, whatever water conservation we can make in the local district there. We can definitely go for our water balance studies in the district. We can account for various uses of water in Okara. And then once we do that exercise in Okara district, that would be upscaled in all Punjab. At the same time, this nexus is very important. Water is, as we know, that water is inextricably linked with energy and food security. So water is an essential input. If we are talking about food security, if we're talking about energy security, that won't come without ensuring water security. So that water is an essential input. We are generating electricity from water, but at the same time, from irrigation department, we are providing this water for chilling purpose of the thermal power and combined cycle power plants. There have been 4 and 5 power plants installed near to our canals, where we are providing about 800 cubics of water for their chilling purpose. At the same time, there have been 4 decades ago, this was not the case, but in last decade or so, we also built run-of-the-river projects. One is Karod hydropower project, one is Azad Patan hydropower project. So that water is being used for our energy. That has to be done very cautiously, because at the moment, this linkage is very important. But at the same time, with this rising population and burgeoning population rate, we have to achieve the efficiencies on the farm scale, on the farm side as well. We have to strike the balance between our supply and demand. We have to strike a balance between our environment and infrastructure developments. We have to strike a balance between our conservation and productivity. So all those balances are to be kept in mind, before doing any strategic decision based on, and obviously, I mean, these tools and these algorithms and these analysis are very important, and those would be helpful for us in future decision making for implementation of the Water Act. Thank you.
Thank you very much, Amar sir, for highlighting that one, the need, and also providing the overview of what are the Punjab Irrigation Department priorities, and how the different tools will be helpful for making that one the shared benefit to all the sectors there. Thank you. And I will come back to you for another question, but let me go to the other is to Dr. Nadeem, that you are representing the government here, and particularly in the Balochistan context there. So what capacity strengthening and institution changes is required to foster a WEFE NEXUS approach within the government circles? Over to you.
Bismillah ar-Rahman ar-Rahim. First of all, I will like to thank you, Dr. Mohsin Hafiz, and the ME team for the invitation, so that we are able to show our points. So what I think is, what is my thinking is that everything what we are doing is that's for the food security. And alarmingly, what we heard in the morning session, there were some very facts which we received, that almost it's about 35% of the inflows of the Indus Basin system that has reduced. That was told in the morning. So it's a very alarming situation in Pakistan. So everything, as you know, that has to be governed through the Indus Basin system, mainly in Pakistan, which covers for the food security. So on that context, what I think that, and also there are some things that the 35% of the water in the Indus water system, after the distribution in the distributaries, they are also lost due to some losses, maybe conveyance or any other losses. And in Balochistan, as far as with respect to Balochistan, it is said that in future we will have to depend on Balochistan in order to secure our food security. So that will be the only option left with us. So if we go towards now and or after 10 years or 20 years after, we will have to take that thing into account. So what we have about in Balochistan, we have about 12 to 14 to 15 million acre feet of water, which is annually lost as in flood water flows and as spate irrigation flows, which we are unable to cultivate, which we are unable to harvest. So what we have to do, we have to conserve that water in order to increase not only the groundwater and also to harvest the water for the cultivation of the crops. And what we can do, mainly we can utilize that water in the form of spate irrigation system. And after the spate irrigation system, we can do for small dams, not big ones, small dams, small water harvesting structures, so that we are able to conserve the water. And what type of plantation are we going to do there? That's not on maybe on the uncultivated lands for the low delta crops, the low delta fruit crops. Maybe that's olives, that's pistachio, which have high economic value all over the world. And also for the grasses in order to conserve the soil conservation. So what I think is that we should take a serious step towards the construction of the small storages in Balochistan, and also which will result in because everything has to be done for the food security. So this was my suggestions, and also we have to strengthen the institutions also, and through trainings and something like that, so that everything is motivated, all the people are motivated. The government institutions are also being taken into account, and they are adopted with the current scenario of agriculture. Thank you.
Thank you very much, Nadeem, for highlighting the need of the capacity development and how to link the better utilization of resources within the Balochistan, which is facing that acute water shortage. Now we're moving to to another panelist, Sahresh Raja. Sahresh, you have been involved in doing a extensive field survey and also getting the information on rural energy and how that's playing a role there. I'm interested to hear more about that one. what are the key findings from the study which you are leading it?
Yeah. Thank you so much, Dr. Mohsin. So I've been engaged in conducting this quantitative survey which was collected in Rahim Yar Khan district of Punjab. The quantitative survey was conducted under the work package 3 of NEXUS Gains initiative by CGIAR. What we did in order to understand the water, food, energy and ecosystem nexus, we conducted this study. And this study was basically based on the quantitative survey of 1,000 household with 1,000 male household members and 1,000 female household members. So looking at the energy excess portfolios and then linking the energy excess portfolios for irrigation in that particular district, we looked at the production diversities in the region, and also we looked at the food insecurities and the food group diversity scores of those households which are actually engaged in different sorts of irrigation, pumping irrigation, which includes the diesel irrigation, the electric irrigation and the solar pump irrigation systems. So what we found from the quantitative survey was that a massive and a huge amount of respondents and the surveyed households, they were using the diesel pump irrigation mechanism for on their farms for irrigating for irrigation purposes. Approximately 40 to 50% of the survey respondents, they reported the use of diesel pump irrigation systems, while only 7% of the respondents out of 1,000 households, they reported that they use solar pump irrigation for irrigation at their farms. So when we looked at these energy excess portfolios that incorporated the electric, diesel and solar pumps along with the non-pump irrigators as well, because we found a huge number of non-pump irrigators as well, and we looked at their linkages with the production diversities, we found that the diesel pump irrigators, they were diversifying their crops relative to the solar pump irrigation. Solar pump irrigators were engaged in monocropping, and that was also the monocropping of cotton crop, which is a water intensive crop. So this can in terms of the policy perspective, this can be considered that while we are moving towards the non-renewable, we are moving towards the renewable energy sources for irrigation, but we also need to look at the excessive extraction of water, of groundwater from the use of solar pump irrigation. Besides that, we also incorporated the impact of the climate shocks on the production diversities, and as we know that the Rahim Yar Khan district, it faced erratic rainfalls in 2021, and because of that, the production diversities were negatively impacted and they were drastically reduced. Similarly, women's engagement in the irrigation decision, they were found, we also looked at the women's perspective in the agriculture practices, and we found that the households who were engaged, whose females were engaged in the agriculture practices, let's say it's irrigation, etc., they had greater production diversity as compared to those farming households where the females were not engaged. So again, this is a policy perspective that whenever the training programs are conducted, we need the gender equality and the social inclusion of females as well in the agriculture sector, and linking that with the energy sector, it can definitely give fruitful outcomes. Besides that, we also look at the food securities of those households, and interestingly, we found that the production diversity, like the growing of different type of crops, it was not reflected in the food diversities of those households. The one reason that we identified was that the crops that were grown by these households, they were majorly cash crops, or they were the staple crops. So the diversification was very less. The production of fruits and vegetables, it was very minimal, and only crops that were cash crops and the staple crops, they were highly cultivated in these regions. So the linkages to the linkages to the dietary diversity from the production diversity, they couldn't be found significant, but we also assessed those linkages through the income channel as well. Let's suppose if the households, they are growing the cash crops, or they are growing crops that are giving high revenue, so what are their impacts on the households food diversity? So we found that although the production diversity channel is not significant with the dietary diversity, but the income generated from these crops, which are highly like cash crops, it was reflected in the food diversities of these households. Moreover, the households where the women were the head of the households, they were found to have high food diversity scores as compared to those where the male respondents were the head of the households. Another interesting finding from it was the households where the energy supply, the electricity supply was adequate and reliable for like near to 24 hours, they had better food diversity scores as compared to those households where the reliability and the availability or the supply of electricity was not efficient. So that were the key findings from that quantitative study we conducted.
Thank you very much, Sahrish, for sharing the practical findings on the ground, because model could do anything, but what's happening on the ground, that's very important, and that could help us in calibration the model to have a better understanding of what's happening. Just on, thank you very much. So now before now we are opening the floor for the question, but I will ask first question. I will ask Habibullah Bodla Sahab, who is sitting here. Well, sir, you have around 30 years of experience of running the irrigation system in Punjab, and you have been part of the development of various models for IRSA. Even your own department, irrigation department, have developed the model and everything. And you have seen the two models. One was presented by Julian, and other is also by Dr. Afrin Sreki. Where do you think that one, for having the complex challenges of Punjab, for multi-sectoral water needs and everything, how we could overcome of the solution? Any comments, critics, positive on the model, on the modeling approach?
Thank you, Dr. Mosa. First off, I would like to comment on the Julian models. Of course, whatsoever he has given the examples of the various countries. In my opinions, the given examples are also applicable to our own systems. We have already developed the models. For example, IRSA has developed the model, CGIAR has developed the model for the IRSA, but in fact it is a statistical tool. Whatsoever the decisions were being taken by the IRSA, the manually, it has been computerized. And similarly, we have also developed a system, water source management irrigation system in the Punjab. That is not the decision support system, in fact. So, with the help of the Julian models, we can develop decision support systems, not only linking the energy and the water, but we can also develop efficient nodal network models. Efficient nodal network model means because our barrages and the dam, they are the nodes. And whatsoever the supply we want to receive at the particular node, through this model, through the artificial intelligence, we can make a better decisions at the nodes, and that will be very helpful for the efficient water distribution systems. As regards the Dr. Arfin, there is only one constraint, because in the system, in our system, the byproduct at the reservoirs is the energy. We cannot give the priority to energy. That is the byproduct. Priority is our irrigations. So we have the limited space for the energy efficiency to improve the energy as regards, because our main focus will remain as the irrigation. But with the help of the efficient nodal network model, definitely we can bring a big change in the system. These are my view about the Julian model.
Do you try to use the simulation model to represent the reality of the system? Or do you try to use, because all these simulations can also try to optimize the allocation, or do you try to represent the allocation? So the question is, is the allocation, that's a social, political, historical reality? Is that something that's available to change or not? The locations we can't change, but in some countries you can't change the allocations either because they're yeah, the efficient network model, yeah, the mathematics can be efficient, but are there, cultural, historical reasons why we don't care about necessarily the perfect efficiency? We want to have some social rules. For example, in Europe, or for example in California, where I did my PhD, there was something called the special species. I forget what they're called. I haven't been in the U.S. many years. Species that were going to be extinct had priority over everything, even public water supply. If you could prove that a biological species was going to go extinct, then they had priority over even basic human needs. And so that, that was decided by a court of law. So Pakistan will also have its equivalent, rules. And so we have to be careful to use the models in a way that optimize what can be optimized, but also represent the reality. So that's why, even though it's quick to make an initial model, it's a big investment to make these models, because you have to really embed, not only the topology, the geography, but also the social, cultural, political reality of the system. And you have to be emotionally and politically intelligent in how you do that, or else you can just get into trouble. So yeah, let's see how well we do.
Thank you, Professor Julian. Dr. Afreen, over to you.
Yes, I think these are all very interesting comments. The one thing I will add on top of what already has been said is that models, as Dr. Julian just mentioned, can optimize any objective that we care to represent and care to optimize. And to me, a more fundamental question is understanding what the objectives are, and then are those objectives really widely shared by all the different agencies and organizations? And then do they widely share or adequately share the necessary trade-offs that are involved? And that is sort of, in my view, some of the bigger and more important questions and conversations that need to happen in Pakistan, right? As Dr. Bodla just told us, that we do have a prioritization. Food security has always been the number one priority. Since the establishment of Pakistan, food security was always prioritized, Sicily. So we do have a categorization, and that's fine. But also then understanding that, are we trying to improve food security, or are we trying to improve incomes of farmers? And that income would then enable them to do many other things that they want. I think those conversations need to happen, and then the important linkages that in my view, are missing need to be established. At least from my understanding, analysis, conversations, research that I've done, what I see is that there are many systems in Pakistan, in water, energy, food, that are running open loop. And by open loop, you saw the diagram that I was showing. There's a whole process of decision making and operations, and then performance assessment that happens. And that's all very sophisticated and detailed. But what is not clear is how much of that performance assessment is being fed back into future decision-making, allocations, and policies. And I think some of those feedbacks and information links need to be institutionally established, and then not only within one sector, but then across the interlinked sectors. And that was one of the diagrams I was beginning to show. I think these institutional connections of information exchange and negotiated discussion on the fundamental objectives that we really want to achieve is important. There are stated goals of water, energy, food security that government of Pakistan puts out, but are we really putting targets for those goals? And are we monitoring how well we're achieving them? That is unclear. And I think those elements all need to be put in place. And until we have that connected system operating, I feel that we're going to continue to fall short of some important objectives.
Thank you very much, Dr. Afreen. Now the floor is open for any questions. Okay.
share of the province share of the at the reservoir level cannot be changed. But as regards the allocation of water within the system, we can change the allocations. Just I want to bring the clarity.
Any other questions? Floor is open. Okay, I think we started very early, around 9 o'clock or 9:30, and it's a long time. So let's, let's move to the next one. I will be inviting the Engineer Mushtaq Gill Sahab, who is the former Director General of On-Farm Water Management, Government of Punjab, and for providing a closing remark. And Engineer Mushtaq Gill Sahab has won many prestigious awards, including the Stara Imtiaz from Government of Pakistan. Over to you, Mr. Gill Sahab. Please join us.
This session was actually leading to a step towards meeting the challenges of the present challenges of climate change, ever increasing population pressure, and the increasing demands for water besides agriculture sector, and plus the requirements from increasing requirements from groundwater. So I think Dr. Julian, presentation of the simulation model, which addresses water, energy, food, and ecosystems approach, giving the excellent 8 examples, which has been done, starting from London, company for abstraction, then East England, then many of these, examples. But more importantly, moving to model which was really, I liked that approach, which was transboundary applications, like Egypt in East Africa, like Egypt purchasing energy from Ethiopia. That was an area which could also that helped also Egyptians to get the continuous water supplies also, and even transboundary issues which were there. Then the typical example of depending, which was besides Amu Darya, there was an example of very interesting example of Ghana, using sun and solar and wind energy, to meet their requirements, besides the Egyptian, kind of thing. These are some of the examples for tackling transboundary governance issues. So in that case, I think then our learned panelists, particularly Dr. I was so happy to know that Engineer Amar Khan and subsequently Engineer Bodra Sahab has mentioned that these are some of the things on which such models are being practiced in terms of whether it's through IRSA approach or CSIRO to, just instead of reinventing the wheel, getting certain things which could be replicated to meet our challenges. So then I think Dr. Afreen Siddiqui, took another burning issue, that was also, affecting our food security challenges, which is really an issue because our major emphasis on water dependence over the years for 100, let's see, 150 years before, when this, when we were a water affluent region with population of hardly 15 million. Now, after 150 years, we are now the water deficit or water scarce or water, deficit situation with population of 225 million, which is 15 times increase. So that has, at that time, 150 years back, entire system was dependent on canal system or this. Now, who could know that there are going to be, there was no concept of groundwater pumpage. So integrated use was not there. The tools of, the present tools, which we are using, like, IoT-based, artificial intelligence tools, they were non-existent. But when the water requirements increased, the groundwater at this stage is a major contributor. So that was, a kind of an other indication where we could, use this water to meet our agricultural use, domestic use, and industrial use. And particularly, it was interesting to note that our use of energy at farm level, this was a kind of a major, a kind of eye-opener that in the morning session, it was indicated that almost 80% of our water is used for growing cereal crops, growing water guzzlers like sugarcane. But I think that study was an indication that how we could bring a balance between the food system sustainabilities as well as, meeting the energy requirement at farm, which are major are through diesel energy or diesel pumps. About 85% of our 1.5 million agricultural tubewells, they are using the diesel energy, and that was just leading to high pumping cost, high irrigation costs, and ultimately, the affecting the water productivity because of pumping saline water. But at the same time, this was our panelists, particularly Dr. Rasool Baksh Kumar Saab has indicated how this model, both models presented by Dr. Julian as well as Dr. Afreen Siddiqui, how this knowledge is being adopted through soil moisture estimation, the salinity assessment, and also the working of agriculture and domestic water requirements. This was the application. This was a happy sign. But then I think the important discussion came from Dr. Sairesh Raja. The study, which was conducted by IFPRI in developing the, water, food, and energy systems in 1,000 villages in that area, how it's affecting, the rural life, normal, food requirements. This was a kind of, I think, and other areas where we could see how these water requirements for water pumping and growing, for taking the decisions for growing crop diversification. This was interesting, that how solar pumping, solar energy is being used for monocrop cultivation like cotton, and moving to low delta crop water requirements. So actually, that a similar study was also conducted recently under the IMIS, program by my organization also, where in 4 villages we could see that farmers are, making very their irrigation decisions intelligently. If that water is not available, from those sources, they are using the, energy sources, solar pumping, and there the decisions are mainly coming from the women folks. So this is an area, I think this actually session, to me, I feel, has set a stage that we can also think of developing certain these models, applications at basin level, and also we can see that in a situation where all stakeholders are there at certain administrative levels, like the example of District Okada was given, where this is whole, this model is being tested. But I think that could be further taken down at taking village as a micro basin or a place where we could involve the all 3 types of water: the rainwater, account for rainwater, surface water, groundwater, and even wastewater to use for, and particularly for rationalizing the demands for agriculture use of water, meeting the crop water requirements. So these are the kind of, this requires the policy changes, this requires the involvement of all these stakeholders. So to me, I feel that this session is, I think, subsequent sessions under this are going to play a kind of a role, which will be, at the end of the day, we can see that how we can make certain changes in the implementation or some, amendments in our enactments or in our rules, whether it's a Water Act or a regulatory framework to involve all the stakeholders, particularly the women folks who are taking these decisions to use the alternate energy sources. Thank you.
Thank you, Mr. Agilsa, for synthesizing, excellent synthesis of that one, the session finding. First of all, I want to say thank you to Dr. Afrin Siddiqui and Amar Khan for joining us online. Thank you, Afrin, for an excellent presentation and sharing some of the innovative ways how we could overcome of the complex challenges. Amar Khan Sahab, I know that when you're fully busy but again sparing your time to work with us, that's really appreciated, and we appreciate your critical thinking and how we could work together to overcome of the complex challenges. And lastly, I will say, Julian, thank you for coming all the way from Manchester. And as we discussed many times, I thought, okay, while you are working from the Manchester, you will not have some of the understanding what the stakeholders are thinking, where we want to build the model. Whether the model is rubbish or model is good, it's important to get the feedback directly from the stakeholders and see how we could develop something which is practically applicable and that could help some of the complex challenges which we are facing. And thank you again for joining. And you arrived 7 a.m. or 8:30 a.m. at the hotel and whole day fully charged. Thank you for your active presentation, and then thank you. To all of my, this team panelists, thank you for your contribution and valuable contribution and sharing some of the practical insights, which we highly appreciate. And lastly, to Mr. Agilsa, we will just go now before we close it. I just want to, we want to have a one group photo of the, again, Julian with you that has come us. But before, I just want to make 2 housekeeping announcements. One is it will be starting tomorrow around 9:30. So I will be requesting again that please join us at 9:30, 9:20 here for this one. They are the session which is mentioned in the program.